Before we proceed into the main part of the presentation with our guest speaker, I just want to give a brief introduction to the Midas e-learning courses, because I see a lot of new registrants here today. So I'll just go over what sort of these e-learning courses are all about. Okay, so what are Midas e-learning courses? Basically, they're an online technical service that we provide here at MIDASoft, and they consist of 3 separate sections: the technical seminar, the in-depth case study and discussion, and the numerical modeling and analysis training. So right now, you are enrolled in the technical seminar, so the first portion of this series. Okay. So why exactly are we opening these courses? So the main reasons are to contribute to our clients as part of our technical services. So here at MIDASoft, we pride ourselves on being able to provide very in-depth technical services, not only technical support for our software, but also offering new opportunities to expand your professional education. Also, spreading technology, obviously, through attending these courses, you learn more about how our software can provide very unique and advanced solutions to your own design projects. And last but not least, to bring happiness to engineers and to lead to breakthroughs. So we've had many engineers who've had experiences where they've attended these seminars and they were able to use our software more effectively and to find different design methods that were able to work for them in their own projects, their own applications. Okay, so the first part, the technical seminar, the main contents, will consist of a guest speaker, a professional engineer from a leading design firm, a DOT, or a university, and they'll discuss a specific bridge project and their considerations and the challenges that were faced and how they were overcome. So the main benefits of the technical seminar: first and foremost, you'll learn first-hand information about the design process from an experienced engineer. So for example, if you don't have much experience with this particular bridge type or these particular challenges, this would be a good opportunity to be introduced to it by a professional or someone who's had a great deal of experience in this project type. You'll also get a technical overview of the design considerations, so all the major points or the main sort of factors that you need to address when creating the design will be sort of went over and explained. And then you'll also learn about significant projects in North America by leading bridge design companies. So throughout these seminars, we'll have various case studies of landmark or significant projects that would be of interest to you. And also networking. So all of our speakers, they're open to questions, they're open to professional networking. So this is an excellent way for you to expand your professional network and to get to become acquainted with other professionals in the industry. Okay, so as you can see, we have a wide range of different guest speakers that come and speak at our seminars, ranging from engineers from leading design firms, professors at universities, etc. Okay, so after the technical seminar, there will be a follow-up session, the in-depth case study and discussion. So the main contents of this session will be covering the technical seminar topic. And detailed discussions on related case studies and the latest technologies. So for example, in the technical seminar, it was just a basic introduction to the topic or to the design. But in the in-depth case study and discussion, it'll be a lot more focused and a lot more specific. So the benefits of attending this seminar, you'll also learn about the advantages of finite element analysis and bridge engineering. So for those of you who are new to finite element analysis, or even those of you who are experienced but want to continue to expand your education in it, this is an excellent opportunity to learn about the benefits of finite element analysis. You can explore different approaches for modeling, analysis, and design of bridges. So once again, we'll be going into not just one specific sort of way to do the design, but also the various options that are available to you. And then also you'll be able to use the latest technology in your everyday design and work. So we'll discuss the various or the latest methods that are used for bridge design, not only with our software but with other practices that are out there, so that you can make sure that you'll be up to date with the latest and the most efficient design methods. Okay, and then last, our third session, or the concluding session, will be the numerical modeling and analysis training. So during this session, you'll receive a step-by-step demonstration of how to model a specific bridge project. So the 2 previous seminars will give you an introduction and sort of a detailed discussion, but with this you'll get a very specific and a very detailed project that you'll learn step-by-step how to model and how to analyze. You'll go over modeling techniques, output extraction, as well as design check codes for satisfaction. So the main benefits are that you'll be able to learn correct numerical modeling. So you'll get to take all the knowledge that you sort of were introduced to in the previous 2 sessions, and you'll be able to apply them specifically to a project. You can learn how to model different types of bridges. So for those of you who want to maybe expand your professional application, this would be a good way to be introduced to different types of bridges. So if you're looking to try out different bridge design projects in the future, this is an excellent way to get started. You can explore concepts of different analysis, so different design methods or analysis methods. You can sort of compare and contrast which ones work best for your project. You can get all the latest updates of North American design codes, and also all attendees will receive free training software. So for those of you who aren't currently users of our software, we'll be in contact with you and we'll give you the opportunity to receive a free trial version of MIDASoft to try out for yourself. So this is just a quick screenshot of what MIDASoft looks like. It's 3D finite element analysis bridge software, so it has a variety of advanced features that help bridge engineers to work efficiently and to save a lot of time. So once again, throughout the course of these series, you'll learn how MIDASoft can provide some very unique and some very advanced solutions for you. And once again, if you're not currently a Midas user, we'll be in contact and we'll teach you and we'll show you how to, you can use the software for your own projects, and we'll give you the opportunity to use it for yourselves. Okay, so before we move on to the main section, I just want to briefly introduce our main speaker. So our speaker today is Andrew DeMiller, PhD. So just some background information on him. He received his master's in civil engineering from the New Mexico State University, and he also received his PhD in civil engineering from the New Mexico State University as well. Currently, he's a structural engineer at Wilson & Company in Denver, Colorado, and he's had a great deal of experience working as an inspector for the New Mexico DOT. And the topic of today's session will be the modeling of a geometrically complex box girder bridge. So without any further waiting, we'll just turn the time over to Andrew. And Andrew, you may begin your presentation. Thank you.
All right, thank you. So today I'll be speaking about the modeling of a geometrically complex box girder bridge. Here's a brief overview. First I'll be discussing the bridge geometry of the structure that I worked on. Next I'll be going into the model requirements, what we needed from these models, the evaluation of various model types, and the modeling approach for both grillage and a plate model. I'll also discuss some of the challenges faced and the solutions I came up with for this project, and I'll discuss the methods that I used for evaluating the data. All right. So here is a plan view of this structure. It's a local bridge over Interstate 70 down here in Denver, Colorado. As you see, it's not symmetric in any real way. You have the flared webs out here that bifurcate. So out here on the wide end, we have 6 webs. Get here towards the middle, we're reducing that down to 4. These webs vary along the same radius, but they terminate at different locations. And if you take a look here, it's not dimensioned, but the web spacings vary from about, I think it's 23 feet right in here, to a minimum of about 16 feet right here in the center. The overhang width varies from about 8.5 feet to a little over 16 feet. And if you'll note these lifting diaphragms here, those were used in, well, will be used in moving the structure once it is completed. Here's a look at a few of the cross sections of this bridge. You'll see that the keyword is varies. Nothing is staying real constant along the length of the structure. I think the only thing that does is the spacing between webs 2 and 3. That remains 16 feet throughout the entire length of the bridge. Just about everything else changes. This illustration up top is showing you a cross-section between abutment 1 and the first lifting diaphragm. In this region, the top and bottom slabs are constant thickness, a foot up on the top, 8.5 inches on the bottom. And then we have the overhangs that vary in thickness and width. In between the lifting diaphragms, this bottom web varies. The way it was constructed, it varies linearly from lifting diaphragm 2 to lifting diaphragm 1, or vice versa. So it's wider, or it's thicker, sorry, at the wider end of the bridge, and it gets thinner as we get towards the narrower side. Then up here, the deck varies in thickness. It's haunched over all of these webs. And then out here, we're looking at lifting diaphragm 2 to abutment 2. This is pretty similar to the other end, where the bottom and top slabs are constant thickness, except out here in these exterior voids, where we're going from 1'3" to 1 foot. Here's a closer look at the web bifurcation. There's kind of a transitional zone here where there's some extra concrete. Take a look at section A. You can see that this gap between the webs is filled with concrete. As we get closer to the termination of this web, this is the cross-section here. So just kind of a summary of what this bridge is. That's a one simple span, a little over 150 feet, 156 feet long. It's a cast-in-place, post-tensioned concrete multicellular box girder. About 6 3/4 degree skew. The width varies from 54 feet to 117 feet, and the web spacing varies from about 16 feet to 23 feet. One thing that made this project interesting is that it is being built off-site and will be moved in place using SPMT equipment. And it was internal and external post-tensioning was used for the structure. Some notable features, especially in terms of modeling this bridge, are the asymmetric flared webs and deck edge as well. The web bifurcations, the varying bottom and top slab thicknesses, it's dependent on location, and the skew of the bridge. Here's some detail about the bridge move itself. This is the equipment that will be used during the move. All these axles here represent the SPMT equipment there. Each of these are mega jacks. These support these load spreading beams, which in turn support the bridge itself. Each of these mega jacks in each group are going to be set to where they have equal reactions. So they'll be hydraulically connected to kind of maintain that requirement. So both of these will have the same reaction throughout the entire move, same as these three together, and these three together. The different groups will have different pressures, will have different reactions, but within each group it will be the same. Here's a brief video showing the move itself. Due to the site where they built it, they're going to have to drive it out onto the interstate and turn it around 180 degrees. You see the blue here, that represents the dirt work that's going to have to be performed between the closing of the interstate and this move actually taking place. And you can see it's going to drive right there into its final location. So now I'll discuss the model requirements, what we were looking for from the models that were created. First thing is really the thing you're looking for anytime you're making a model. We're aiming for a realistic distribution of forces, especially during the SPMT move. looking for a good idea of the forces in the diaphragms. We wanted accurate bearing reactions, considering the elastomeric stiffness. We're looking at the displacements due to external loads and post-tensioning. We also wanted to know about the global torsion and the final condition, and we're especially looking at this during the move. And we were designing a bridge, so we're looking for beam shear and moment. The way it was designed, each web line was designed individually. So the webs were divided using the effective flange width. So from the model, we needed the shear and moment. So here's a little evaluation of the various model types that were considered. Spline model wasn't considered real closely. This is the simplest model. Gives no information for the diaphragm loads. It's difficult to model the web bifurcations well. The shear and moment for each web are not available. Just gives you the one value for each location along the length of the bridge. The load distribution is not modeled well. Bearing reactions are not modeled well. And the post-tensioning, as a plus, post-tensioning can be modeled in there. Next step up is the Grillage model. This is a relatively simple model. The diaphragm loads are not as accurate as those from a plate model. In this case, we can model the web bifurcations with a little more accuracy. The shear and moment for each web are readily available from this model, so that was a plus. The load distribution is not modeled as well as it was in the plate model. It doesn't consider all of the everything that's going on in this box girder. The bearing reactions were not as accurate as those from the plate model, and the post-tensioning can be modeled well using the Grillage model. Taking a look at the plate model, this is the most difficult to model. The most difficult model to, I'm sorry about that. All right, the most difficult model to create and evaluate. It's the most accurate in terms of the diaphragm forces, in terms of the load distribution, and for the bearing reactions. Kind of the negatives of the plate model were that the calculations to obtain shear and moment for each web involved the output from many plates and required a fair amount of work to obtain those. And the post-tensioning could not be modeled accurately. So the models selected for this bridge were a Grillage model and a plate model. We used the Grillage model to ensure reasonable results from the plate model. That was important since going into this, the plate model is fairly complex, so it's worthwhile to put forth a simpler model to validate what we're doing in the more complex model. I used the Grillage model to get information about the post-tensioning, so that was looking at losses and also deflections. And also the bridge rating was performed using the Grillage model. Main reason for that is that the model input and output were far more easily interpreted than the plate model. And I felt that was a worthwhile goal when considering the bridge rating. The plate model was used mainly for the design calculations, including web shear and moment, global torsion, the elastomeric bearings, and the diaphragm design. This model also came into play for the move condition. I feel it was very important when considering this move condition, since it did do a good job considering the different variables at play for this bridge. So the modeling approach. First model created was the Grillage model. First step was to determine the node locations. Next is to create member cross-sections. The south half of the bridge has at least one dimension varying with respect to distance along the bridge. As a result, there were many unique cross-sections. The next step was to create elements and assign cross-sections to the elements. Then the boundary conditions could be put into place. So that's the point springs for the bearings and the rigid links to connect the two exterior webs together at the bifurcation, and also to connect the top and bottom slab for the transverse elements and connect the transverse elements to the longitudinal elements. Next, the loads had to come in, and the post-tensioning and the construction staging to get a good feel for the time-dependent effects on this structure. So here's kind of an overview of the grillage model. The top image is showing you the grillage model longitudinal members only. So you see here, Midas allows you to take a good look at the geometry you're putting in. Each of these cross sections was entered individually. All right, and then taking a look at the transverse members here, we have the top slab, bottom slab, the end diaphragm, and the lifting diaphragm. Looking at the plate model, first step was to determine the node locations. This required significantly more effort for the plate model than it did the grillage model, since there are many more nodes, more things needing to be defined. Next step was to define plate thicknesses to represent the concrete along the bridge. Then the elements needed to be created and the thicknesses assigned appropriately. Next step was to input the boundary conditions. So rigid links were placed between web W4 and 4A. So again, at the bifurcations, they're rigid links. And then the elastomeric bearings were modeled using point springs. Next, the loads were put in, dead loads and live loads. So here's the plate model that I created for the structure. This top view shows, as you would be looking at the bridge from an isometric view, you see the bearing diaphragm out here at the end. On the top, you see all the deck elements, and then you can kind of see the diaphragm poking through here too. Here is a view with the top deck listed off, basically inactive, so you can see the webs and the diaphragms with more detail. You can see in here, these are the lifting diaphragms, and then you can see along this web where the bifurcation takes place, these webs were thickened to represent that transitional area where there was more concrete placed to kind of stiffen up and strengthen that connection. Same thing over here. So some of the challenges encountered. Grillage model wasn't too bad. Main hang-up was the creation of member cross-sections and changes in geometry, so those kind of go together. In terms of the plate model, there's obviously the geometric complexity, so that involves some time getting the node locations and assigning the thicknesses appropriately. Data interpretation required much more effort than with the grillage model. The beam, shear, and moment for each web were not direct outputs from this model. I'll show you later how I put that all together. Global torsion as well, same kind of thing. And then for the move condition, had to determine kind of how to evaluate that, looking at the maximum twist and the effect on the bridge as a whole and on the diaphragms. So here's some solutions, the way I solved them. For the grillage model, the creation of member cross-sections was aided using a drawing in MicroStation. So I used the plan that was created by the drafter and created a drawing with dimensioned section segments. I entered these dimensions for each segment into Midas. I chose not to use the section property calculator tool that they have. This was mainly so that I could check the geometry as I put this model together. Name the cross sections for easy identification. So, for example, I guess this kind of letter string here represents Web 2, Section 2, so W2S2, lifting diaphragm to transition 1. Transitions were the start of where those webs were thickened as the webs came together on the exterior webs. Since most segments were tapered, the cross sections of each web at each location were changed, location of change, and the geometry were entered. Then those sections were copied to the tapered section to reduce data input. So here's kind of a look at what I'm talking about. So this is a screenshot of the drawing in MicroStation. Up at the top was the plan view of the structure. I used that to bring straight lines down to mark the locations of the webs at the top of the deck. And from there, I could use the typical sections to draw out the rest of this cross-section. Once I had that, I copied all this over here and broke each of those full cross-sections into the various segments. So there's 6 webs, or 6 web lines up here. It includes the web itself and the effective flanges. Then out here where the bridge narrows, there's only 4 web sections per location. I labeled these back wall to lifting diaphragm 1, I end and J end. So this is basically at the back wall or above the supports, and this is at the lifting diaphragm on this side of the lifting diaphragm before the bottom slab thickness begins to vary, and similarly for the remaining sections. Here's a close-up on one of those sections. I believe this was the first location. So this is that exterior web section with all of the relevant dimensions labeled, which were subsequently put directly into the MIDAS software. Now taking a look at the plate model. First step was determining the node locations. The bridge was divided longitudinally along its skew to include nodes at the changes in geometry, such as the web transitions and bifurcations, changes in deck and bottom slab thicknesses, 10th points, and also at 10th points for the design calculations. The node locations at the webs at the top of the deck were measured relative to a reference point and entered manually into a spreadsheet. From there, I was able to calculate the remaining node locations. When possible, nodes were placed in the same location in the plan view for the top and bottom slab. In the top slab, nodes were placed at the end and middle of the deck haunches. Nodes were placed to maintain similar plate dimensions along the width of the bridge. Was aiming at square elements as much as possible. Some locations that didn't really work out. The nodes were placed such that slabs could be easily divided for calculating web moments. So you saw a couple slides ago we were looking at the cross sections that were broken up into various elements. Made sure that there was a node where those elements were divided. And then here is the plan view of the plate model. So in terms of thickness assignments, the average plate thickness was used when there were tapers. Nodes were placed at the center of gravity of all plate elements. The beam, shear, and moment for each web, the output that we were looking for was beam, shear, and moment for each web element, which consisted of the web itself and the effective top and bottom flanges. The plate model provides the following outputs. We're looking at forces or stresses per unit length at each of the node locations. The total force at each node location for each plate. And there's also a tool called the local direction force sum. So this gives forces and moments along or about 3 axes. The axes are defined in the process of defining the line along and about which the forces are summed. So to get the desired output from the model output, had to combine the axial forces in the flanges with the flexure and eccentric axial force in the web plates to get the total moment for each section. The forces in the flanges from the plate force tables were used. So for each of the flanges, I was able to put together a spreadsheet using tabular output directly from MIDAS. The web forces were obtained using the local direction force sum tool. A large spreadsheet was used to efficiently convert the output from the individual plates to the beam shear moment that we're looking for. The moment was determined as follows. So your moment is equal to the force in the top flange times the distance between the centroid of the top flange and the centroid of the section as a whole, plus the force in the bottom flange times the distance between the centroid of the bottom flange and the centroid of the section as a whole, plus the moment in the web that was pulled out using that local direction force sum, plus the axial force in the web times, again, the distance between the centroid of that web and the centroid of the section as a whole. To get global torsion, this following equation was used for that. The torsion in thin wall sections can be determined using this equation. So your torsion is equal to the sum of A sub I, which is the area enclosed by the center line of the elements surrounding the ith void, times Q sub I, which is the shear flow in the ith void. The shear flow in the webs included both the beam shear and the torsional effects going on. So that caused the shear to increase on one side while decreasing on the other. Instead of trying to separate those two effects for the webs, I chose to only consider the top and bottom slab plates in calculating that torsional moment. Then looking at the move condition, in terms of the allowable twist, the global cracking, or the global torsional cracking and diaphragm over stress were used as criteria. In order to do this, the supports were placed at each web location at each of the lifting diaphragms. A unit twist was induced at the narrow end of the bridge at the lifting diaphragm using the specified displacement feature within MIDAS. So this twist was entered by entering these specified displacements along a line. So all four were displaced. The two on the left side went up, the two on the right side went down along a line. So the twist angle was then scaled to reach the cracking torsion, and the twist angle was also scaled to reach diaphragm failure. So obviously the forces, the global torsion needed to be calculated, and the diaphragm loads needed to be calculated under a unit twist and then scaled. So here's this section is kind of what I was doing a lot of the time for this project. It's the data evaluation. So the Grillage model yielded the required results directly. So we were looking for shear and moment. That was a direct output. We were looking for displacements. Again, that was a direct output. The live load forces, in some cases, required the use of the live load tracer feature. So when you're considering shear, you want to use the same truck location that's giving you the maximum shear to get you the moment at that section when you're using the modified compression theorem to calculate your shear resistance. The plate model data required processing to yield the desired results. Spreadsheets were set up to process the data efficiently, and the live load forces required, again, the use of this live load tracer feature. I mentioned this a couple times, so here's kind of a description of what this tool is. So envelope forces potentially are inaccurate since the maximum force in one plate may be controlled by a different load case than another plate in the same segment. So part of the process for getting the moments along the webs was getting the axial force in in the plates that made up the top flange. So in that top flange, there's maybe 10 different plates. It's possible that that axial load is maximized in one plate by a different truck location than another plate within that same segment. So you'd be overshooting your moments if you used envelope forces for everything. The live load tracer gives the live load that maximizes a force effect at a specified node of a specified plate. Like I was saying, there's multiple plates that went into determining the moments in this structure. So part of the process was determining which truck location maximizes the overall effect, the shear moment or torsion, when different truck locations are indicated for a single element. The truck location that was given using this tool was then entered as a load case. Here's kind of an image of this tool at work. You can see that it's kind of color-coded. There's the contours. This indicates the influence surface for this bridge. The little blue lines indicate point loads representing the lane loads, and these red kind of flags represent the trucks. You can see that this is meant to maximize the force in one of these top plates out here towards the middle, right in this area. So you could grab this. Midas gives it as a text file, which can later be input as a load case. So if I'm trying to maximize moment in the web that sits under here, and I found that this was the controlling truck location, I could export these loads and then import it again as a load case and use that to calculate the moment in shear. Alright, so spreadsheet I use for moments. A significant amount of data is required. The kind of first step is the data reduction sheet for the flange forces. One sheet was created for both the top and one for the bottom at each of the 10th points. The raw Midas data output was entered, and the total force in the flange kind of automatically calculated from there. So I was able to copy a table from Midas, paste it in my spreadsheet. It would update the flange force for that location. And then there's the compilation sheet, so that takes all of the results from these. I think there's 18 of these, since I didn't do the either end of the bridge for a moment. So compilation sheet takes all 18 of those spreadsheets, extracts those flange forces, and also allows me a place to put the local direction sum results from the webs. So the summary sheet shows shear and moment at 10th points along the bridge. This is the final sheet, which gives the results that were needed for design. So here's kind of a screenshot of one of those kind of data reduction sheets. Here we have the raw Midas data. So I selected the plates that were relevant to this section. So this is the bottom flange at lifting diaphragm 2. So all of these plates were needed for that location for the moments. And then here, I guess before I go to that, there would actually be 4 of these, since this is for live load. The load case here is for the HL93 truck at lifting diaphragm 2, with the truck placed to maximize moment in web 1. So there was a different truck location to maximize moment for web 2, so those results were copied over here, also for web 3 and web 4. And then over here, that was reduced a bit by determining which plates are associated with which web. So plates 3135 down here to 3435 were associated with web 1. So the results for web 1 are all here. And then for web 2, plates 3485 onto something else down here were associated with web 2. And here are the results for that. From this table, I created this table, which boiled it down a little further. So for each web, there are the elements here, which load case was used, just to avoid any errors. I could verify that for W1, we're looking at HL98.3 load for lifting diaphragm to maximum moment for web 1 here, and then for web 2 here, similarly for web 3 and web 4. Only some of these nodes were used for obtaining the flange force. That's because we were essentially cutting the structure along a line. So I only needed to consider the nodes that lied on that line. So that's 6136, 6586 here, all the ones in bold. You'll notice up here that there's kind of a string of numbers that was used to kind of simplify the process of getting results out from MIDAS. I could copy this, paste it into MIDAS where it asked for which elements you're looking for in terms of the plate forces, and then you would get these tables here, which would then update all of this, and you would get the flange forces, bottom flange forces, for each of the webs. So again, this sheet was duplicated for the top and the bottom for each of the 10th points, except for the ends. From those, this sheet was used to kind of extract that data and summarize it a bit. So let's take a look here at the 20% location. In the top of the slab, there's a 200, about 50 kip force in compression. In the bottom of the slab, 76 kips in tension. Here it shows the Z location of the centroid of the top and bottom slab and of the web. And then these inputs were input using that local direction force sum tool. So I could get the shear, the moment within the web, and the axial force within the web, along with its Z location, this location of its centroid. Up here is the elevation for the center of gravity measured from the bottom of the bridge for each of the webs at each of the locations. These were all extracted from the sections that were created for the Grillage model. So the final result uses all of the data that was entered into here and here, as I mentioned earlier. So your moment is the moment in the web plus basically the sum of all of the axial forces times the distance between those axial forces and the centroid of the section as a whole. The shear comes directly from that prior sheet. That's just a straight entry. The moment used this equation. And then the spreadsheet was created for each load case. So there's HL93 trucks positioned to maximize moment, one where the HL93 trucks were positioned to maximize shear, and then one for all the dead loads, and then also for the permit truck. Spreadsheet for global torsion. The average shear flow in each bay was calculated from raw data from MIDAS. A sub I was calculated in MicroStation using that drawing I showed you earlier that had all of the cross sections for the various locations. And a summary sheet was used to tabulate and chart the torsion at the 10th points. So here's the spreadsheet for global torsion. This is the raw data from Midas for the HL93 loading at the 50% location, and the truck was placed to maximize torsion at 50%. You see here there's the various elements that are associated with the 50% location for all of the top plates, and each of the nodes along with the center. We have the shear flow and then the force per foot for each of the axial directions. From that raw data, I could put together this spreadsheet, which kind of summarizes that data, takes only the nodes that are relevant, and use VLOOKUP to get the appropriate shear flow values. Since they were not constant along the width of the void, an average was taken. So there was an average value for cell 1, cell 2, and however many cells were at the given location. These are referenced up here. So you have 2.22 for cell 1, Q sub I, for cell 2, 4.32, and then A sub I, again, that was taken directly from the microstation drawing. And then the T sub I is the contribution to torsion for cells 1, 2, and 3. The sum of that is the torsion at that cross-section. And here's kind of the summary sheet for the global torsion. Gives you the location, the torsion if you're using only the top plates, torsion if you're only using the bottom plates, the average of those two values, and the maximum of those two values. And then here I plotted out the maximum and average for each. That's just kind of to get a feel for how torsion was distributed along the length of the bridge, and to see if there were any outliers. For out-of-plane bending and interface shear, these were pretty much direct output from Midas and just compiled into a spreadsheet. So labeled where different elements were that were kind of throwing off the values, causing them to be much larger or much smaller than for the rest of the structure, such as the diaphragms and the bifurcation. Last thing I'll talk about was the evaluation of the move condition. The heavy lifting contractor proposed a certain arrangement for the SPMT equipment. This was shown towards the beginning of this webinar when we were looking at the geometry of the structure. So there's a load spreading beam placed between the bridge and the megajacks. The megajacks were placed beneath each of the spreading beams. The megajacks were hydraulically connected under each of the beams. To model this, took a little bit of manipulation of the support stiffnesses. If rigid supports were used, the reactions were not equal, but during the move, that will be held constant. Those forces along each of the load-spreading beams will be forced to be equal since they are hydraulically connected in each group. Point springs were used to kind of force this condition into the model, and the stiffnesses were adjusted to equalize the reactions at each of the megajacks. From there, the reactions at each of the webs, the bridge itself, could be checked, and the deflection along all of the diaphragms could be checked. So that's for dead loads, post-tensioning, creep, and shrinkage. We wanted to see how much this bridge is going to go up or go down at the end due to the different loading conditions. So the contractor moving the bridge would know how high he'll need to lift up the structure to get it onto the bearings. So a couple conclusions. The plate model, in my opinion, should only really be used when the geometry and required information precludes the use of simpler models. The results from the Grillage model and plate model did compare well for longitudinal shear and moment. But again, we did need more information than that. We were looking at the move condition, which required a little more of a detailed model. And we were interested in accurately obtaining the bearing reactions along with the diaphragm forces. The Grillage model was definitely simpler to create and far simpler to interpret. If a plate model is required, I recommend that spreadsheets be used to automate much of the input, especially if you're looking at a bridge like this where the geometry is irregular. It's probably the easiest thing to do that in a spreadsheet rather than trying to do that in the graphical user interface. Other kind of tip is to create spreadsheets to use the MIDA output as efficiently as possible. So those are the spreadsheets I showed you for getting shear and moment and global torsion. I was able to kind of grab the tables out of MIDAS, copy them into the spreadsheet, and it would update the forces that I was looking for. Well, thank you very much for logging on. If you all have any questions, feel free to ask. Let me see if there's any on there now. All right, let's see if I can maximize that. All right. Okay, so got one question here. All right. Flipped out, sorry. Okay, so first question was, when you calculated shear and moment in your model, was there any iterative process to optimize your cross-sections? There wasn't. We just took the essentially the effective flange width for each of the cross-sections. Next question. Here it says the geometry was essentially set for the analysis. There were changes along the way. That was definitely consumed some time when there were changes to the geometry. Let's see. Model. All right. Then next question. Long overhang is permitted. This deck is post-tensioned transversely as well as longitudinally, so that's going to help with those significant overhangs there. How much time did it take to complete the whole process? Modeling in MIDAS to results from Excel sheets. All right, so I was mainly on this project from about May to October. Most of that time was creating this model and getting these various outputs out. So for a single kind of to finish an entire spreadsheet to get all of the moments at all of the locations, for dead loads that took maybe a day. For live loads, I had to go through and find the truck arrangement that would maximize the shear or moment, whichever I was looking for, at each location using that live load tracer. So that alone took probably about half a day in itself, and then I had to take those results out of MIDAS, which took about as long as it did for the dead loads. All right, I don't see any more questions on there, so I guess you have a few more seconds if you'd like to add anything else. Otherwise, thank you very much for coming. That looks like one popped up. Do you use MIDAS to rate the diaphragm? We did not do a load rating on the diaphragm. There was only a only a rating, kind of a typical rating produced for the structure. One more question on here. How much did the bridge cost to build? I actually don't know the answer to that question, and it's currently being built. So. All right. Well, that looks to be about it. Again, thank you very much for coming.
Okay, everyone. Well, thank you again for attending today's online seminar. So if you have any further questions or suggestions, feel free to email us at webinar@MIDASuser.com. Also, we do post recordings of all of the sessions that we have on goodengineers.com. So just check that site shortly, and we'll have the recording posted up for you all if you want to review this session once more. And then also we have 2 more follow-up sessions. As we discussed, there'll be an in-depth case study as well as modeling training. So we'll give you more information about those sessions in our emails. But thank you once again for attending, and we hope that you all found this presentation useful, and we hope that you all have a good day.